Assalamu alaikum. Welcome back to EE340. In the previous lecture, we talked about waves in general. Now we're going to talk about electromagnetic waves. So electromagnetic waves propagate in media that are neither perfect dielectric nor perfect conductor. So remember, a perfect conductor is a conductor with a conductivity that's infinite. A perfect dielectric is a dielectric with a conductivity that's zero. In many cases, this is not the case. So we have a dielectric with a non-zero conductivity. This non-zero conductivity will cause some power dissipation. Therefore, the wave will not propagate forever. The wave will experience attenuation. So what we want to do in this lecture, we want to find a general expression for the electric field in a lossy medium. So the very first step is to start with Maxwell's equation. So remember, we have four set of equations that are called Maxwell's equations. We'll assume that the medium is charge-free, so the medium is not a conductor. And also we assume that the electric field, or the field in general, is time harmonic. Those analyses can be extended to a non-time harmonic field, but this extension is beyond the scope of this class. So we have the four set of equations. We have the four equations here, and remember, if we have a perfect dielectric, then the conductivity will be zero. So this equation will look like following. If we manipulate these four equations and we express them in a single, express them in either electric field or magnetic field, we will end up with this equation. This is known as Helmholtz equation. It's named after the German physicist Helmholtz. So the Laplacian of the electric field minus gamma squared times the electric field is equal to zero. So gamma squared is given by this expression, and gamma is complex, so it can be decomposed into two components. We have the real part and the imaginary part here. So the real part, which is alpha, is called the attenuation constant, and the unit is newtons per meter. The imaginary part, this one should be beta, is called the phase constant, and the unit is radian per meter. So now let's solve for the electric field. Let's assume that the electric field has the following form. So the electric field is time harmonic. It's a function of z, and it's along the positive x axis, along the ax direction. Remember, this is not the direction of propagation. The direction of propagation will be along the z direction, as we will see soon. So if you substitute this expression into Helmholtz equation, we'll end up with this formula, and if we solve for it, we'll end up with two solutions. The first one is the forward going wave. The second one is the backward going wave. So in order to, because this is a physical system, so the energy cannot be infinite at z equal to infinity. Therefore, E minus should be zero. and we'll end up with one solution here. If we convert it back into time domain, then we can express, actually we can write this one before conversion as a plus exponential minus alpha z exponential minus j beta c. So this one is a constant, and this one, if we do the inverse phasor transform, we will end up with this equation. So in this course, we assume the wave is a plane wave. So if we know the direction, or if we know the component of the electric field, and we know the direction of propagation, we can know the the direction or the component of the magnetic field. So we can use the following equation here. So in our case, AE is the unit vector in the direction of the E field. AH is the unit vector is in the direction of the H field. AK is the unit vector in the direction of the wave propagation. So in our case, E field is in the AX direction. The wave is propagating along positive AC direction. So AH must be along the positive AY direction. Now we know the direction of the H field, so the magnitude of the H field can be found using the following relation. So the magnitude of, or the final expression for the magnetic field can be found using the following relation. So the magnitude will be the magnitude of the electric field divided by the absolute value of eta, and the phase should be changed by theta eta. So what is eta? Eta is the intrinsic impedance of the medium. So if we have a free space, this one, as we will see soon, I will see in the next class probably, this one is 377 ohms approximately. So this is the expression. We see here that this one is in general a complex value. So it has a magnitude given by the following expression, and it has a phase given by the following expression. So the angle theta E goes between 0 and 45 for two reasons. First of all, tangent goes between this one is negative 90, this one is positive 90. So these quantities are always positive. So the conductivity is positive, the frequency is positive, and the permittivity is also positive for the media that we are going to consider. However, once we go to metamaterial or double negative materials, the permittivity can be negative. So if it's positive, it means theta eta should be in this region. Since we are taking half of that, so the interval will go between 0 and 45 degrees. So now let's talk about the final thing here. Let's talk about the loss tangent. So the previous analysis were derived using the concept of non-perfect dielectric material. So if the dielectric is perfect, as we mentioned earlier, Ampere's law should be like this. However, since the medium is not a perfect dielectric, so we have two components. The first one is the conduction current. The component of this one is the conduction current density, J. This one is the displacement current density, JD. So if the medium is perfect, then we should not have a conduction current density. Why? Because for perfect dielectric, sigma should be 0. However, since the medium is not perfect, we're going to have a conduction current. This conduction current is responsible for losses, for energy losses. If we take the ratio between the magnitude of the conduction current and the magnitude of the displacement current, we will end up, this is known as the loss tangent. So tan theta is known as the loss tangent. Theta is known as the loss angle. And remember, we don't have anything constant anymore, since everything now will be a function of frequency. So in some materials might be a good dielectric at very low frequencies, but they are not as good as they were at very high frequencies. As an example, if we know that most of printed circuit boards, PCBs, they use fiberglass as a substrate material. So this one is known FR4. This is good for a very low frequency, of reasonable for frequencies that in the range of 1 to 3 gigahertz. However, if you wanna go to frequencies that almost in millimeter frequencies, say like 24 gigahertz, and this is FR4 is really a very bad choice. So that's why FR4 usually is the cheapest one. So if you were to design a circuit that operates at high frequencies, at millimeter frequencies for example, you have to go for very expensive materials. One example is Rogers substrates. There are multiple types of Rogers substrate. And the point that I want to show you here is that if you're looking for the loss tangent, you will see here that this value is given at specific frequency. So the values actually is function of frequency. So the loss tangent is actually a function of frequency. So we should be careful when we choose the material for our substrate. The last part is if I can express Ampere's law as follows, then I can combine these two terms and lump them into one term called epsilon C. Epsilon C is actually something called the complex permittivity, and it's defined as follows. So it's a complex quantity, so it has a real part and imaginary part. So the imaginary part is responsible for losses. So remember, the complex permittivity can be written as 1 minus the loss tangent. So the ratio between the real and imaginary part is actually the loss tangent. We will solve some problems in the next video.